Today we're going to start talking about ceramics. So up until now, everything we talked about mostly applied to metals because metals is such an important part of material science, but more and more other types of material are becoming much more important in our everyday lives. So things like ceramics, polymers, semiconductors, right? Those are the topics I would like to cover between now and the end of the semester so that you have a broader understanding of those materials and their behavior, what controls their behavior, and also their applications. So we'll start with ceramics. Ceramics are a metal and non-metal compound material. A metal element plus a non-metal element. And depending on where these elements sit on the periodic table, they could be mostly ionic in terms of bonding or mostly covalent, right? So if they're similar in electronegativities, you can have covalent bonding, such as in zinc sulfide or silicon carbide. So those will have mostly covalent bonding because they're very similar in electronegativity. Metal ceramics that have mostly ionic bonding include magnesium oxide and calcium fluoride because they're far apart on the periodic table. They're very different electronegativity, so they have mostly ionic bonding. And then you have lots of other ceramic materials that we've already talked about, like alumina, Al2O3, aluminum oxide, titania, TiO2, or titanium oxide. Those all have a mixture of covalent and ionic bonding. So let's talk about ionically bonded ceramics first. So if you have ionic bonding, that means what happens to the electrons between the elements? Or the characteristics of an ionic bond, what is it? It's brittle, very good. And why is it brittle? High stress? Oh, strength, right. Yes, so why is it high strength and why is it brittle?
Because the electrons are located.
Right, because the electrons are localized, right? They can't move. The reason why the electrons can't move is because ionic bonding results from a transfer of electrons. Right, so when you have ionic bonding, you have one element that's very electropositive, so it wants to give away electrons. One element that's very electronegative, so it wants to gain electrons. So they bond by transferring that electron from the electropositive to the electronegative. So that's how that bond is formed. And unless you can give the electron back, it's really hard to break that bond. So the electrons are kind of stuck where they are. They can't move around. And so it's difficult to break and reform the bond. So therefore, the material has very high strength because the bonds are difficult to break. But also, because they're difficult to break, you can't really have slip or dislocation movement. And that's why they're brittle. Okay? So the ionic characteristic of the bond is what makes the ionically bonded ceramics brittle and strong. When you have a transfer of electrons, so let's take magnesium oxide as an example. Okay, magnesium sits in row 2. This is, and oxygen sits in row 6 on the periodic table. So how many electrons do you think magnesium wants to give away in order to be stable? 2, right? So you end up with magnesium, 2 electrons goes to oxygen, right? And oxygen also wants 2 electrons because it sits in row 6. It needs 2 more electrons to have a full outermost shell. So you end up with magnesium 2 plus and oxygen 2 minus. Because magnesium lost 2 negative charges and oxygen gained 2 negative charges. Together, they're neutral, but if you were to separate them, you have a positively charged ion and a negatively charged ion. So a positive ion is called a cation, and a negative charged ion is called an anion. So in this case, our magnesium is our cation, and our oxygen is our anion. So our magnesium oxide, a lot of ceramics, especially the simple ones, also have crystal structures very similar to our metals. FCC, BCC, simple cubic. Okay. But we have now two elements, not just one, right? For most of our metals that we've looked at, aluminum, iron, we're talking about one element that fulfills a crystal structure. But now we're talking about two different elements coming together and forming a crystal structure. So what does that look like? So magnesium oxide forms what is called two face-centered cubic. Okay, and I'll draw this for you. So both elements occupy the face-centered cubic structure. This is one. And the second one, it's also the face-centered cubic, but shifted over. So instead of, obviously, it can't be right on top of each other, because then there's no space for the atoms to exist. So the other one, instead of being here, is shifted over 0, 1/2, 0, in terms of the unit cell, right? So shifted. And this one is shifted half along the Y. This one as well. This is from the next unit cell. So you end up with these edges in the middle of the edges. And then this one, the face-centered one, gets shifted half, so you get a body-centered here. Okay, so that's what the magnesium oxide structure would look like. Which element, the way I've drawn this, I drew a big atom and a little atom. Which one do you think would be the oxygen, and which one do you think would be the magnesium? Any guesses as to which one would be the bigger one, the bigger atom? Oxygen, why is that?
It has more electrons and therefore bigger times.
Correct. So oxygen actually has 8 protons. It has an atomic number of 8, so it has 8 protons. And normally we also have 8 electrons, but in this case, because it gained 2 electrons, it will have 10 electrons. Magnesium has an atomic number of 12, but it's losing 2, so it has 10 electrons as well. So why would oxygen be bigger? They have the same number of electrons, and magnesium actually has more protons. But if you remember the way we draw atoms, we usually draw atoms as here's our proton and here's our electron, right? So the protons actually do not contribute that much to the size of an electron because it's a nucleus, and that's not how we measure the size of an atom. It's the outer edge of that electron cloud that we're looking at. Okay. And because that's where the interaction between atoms occur. They don't occur at the nucleus, they occur at the edge of the electron cloud, the outermost electrons. So for magnesium, before it bonds with oxygen, it has 12 protons and 12 electrons. It loses 2 electrons through bonding, and so now it looks something like this. The protons are still the same size. You still have 12 protons, but now you have 10 electrons out here. And so you have a higher positive charge compared to the overall negative charge. So it's going to draw the electrons closer to itself. So that electron actually gets drawn in more because there's more positive charge. So that atom actually shrinks. changes size, becomes smaller due to losing 2 electrons. And oxygen goes the other way. So if we have oxygen, this is our oxygen, 10 plus, 10 negative. It gains 2 electrons. Now you have more negative charges in the electron cloud compared to the nucleus. So the nucleus used to be able to hold all the electrons in, but now you have more negative charges, and those negative charges are repelling each other, right? The electrons don't want to be close to each other, so they push each other out. And so your atom actually gets bigger by gaining electrons. So it's not just the number of electrons, but it's the balance between the positive charges in the nucleus and the negative charges in the electron cloud. So in general, not always, depending on the size of how many electrons these elements have, in general, your anion will be bigger than your cation, because anions have gained electrons and cations have lost electrons. So here we have our O2 minus and our Ng2 plus. I can also draw the same crystal structure with my magnesium as the corner atoms. The unit cell will be the same size. And my magnesium would be in the middle. And then one in the middle. So these two are actually the same unit cell, just depending on where you're looking at it, right? Okay, so there are 2 FCCs that are just shifted slightly with each other. Draw one more way to visualize this. If we were looking at this just 2-dimensionally from the front, it would look something like this. Okay, so you have an FCC here, and you also have an FCC here. Let's use this one as our reference. How many oxygen anions do I have in that unit cell? How many corner atoms do I have? Okay, 8 corner. Each corner atom is shared by how many unit cells? 8 other ones, yeah? Okay. And then I have how many face-centered atoms? Each face-centered atom is shared by 2. So I have 3. So I have a total of 4 oxygen anions. How many magnesium cations do I have in this unit cell? So in this unit cell, I have these ones that are edges, right? Along the edge. How many edge ones do I have? 12. And how many unit cells share each edge atom? Let's say this one. It's shared by this one, the one on top, right? And then the 2 in front. So 1/4. And then I have one more in the center of the unit cell. So center. So we have 4 magnesium 2 plus. So it's a ratio of 1:1 or 4:4, which is good because our magnesium oxide chemical formula is a 1:1 ratio. So if our structure didn't match our chemical formula, we would have some issues, right? It wouldn't make sense. So we have a hypothetical material XY. I'll tell you that X is in row 1 and Y is in row 7. So do you think this material will be ionically or covalently bonded? Most likely. Ionic, they're very far apart on the periodic table. They have very different electronegativities. Good. And Y has an ionic radius of 200 picometers, or 200 times 10 to the negative 12 meter. And I tell you that has this kind of structure. It's also called a rock salt. So XY has a structure that's very similar to magnesium oxide, 2 FCCs overlapping by 0, 1/2, 0. Okay? So I want you to calculate what is the minimum size of X plus that would allow it to fit in this rock salt structure. So not the maximum size, but the minimum size. And the way we would get to the minimum size is if this is our FCC, we're looking at it from the front, right? The minimum size for this is our Y, our X would have to fill this space. That's the minimum size. The reason why that's the minimum size is because if we had a smaller X, the anions would be touching, but the cation and the anions would not be touching. So this is not stable because the anions will repel each other, right? Things of like charges don't want to be that close together. The reason why this is stable is because the cation is attracting the anion, so it's holding it together. But if the anions were closer to each other than they are to the cation, then they would be pushed apart. So in order for this structure to be stable, the cation has to be at least fill the space in a structure like this. It could be bigger. So if you have something like this, that would be fine because the anions and cations are equal distance to each other. But the anions cannot be closer to one another than the cations are to the anions. Okay? So this is our minimum. This tells us our minimum size of X. So how do we find what is the minimum size of X that would fit into that structure? How would you solve that problem? So I will use this picture, because that's what it has to be. This is the minimum, right? So I'll use this picture, and I would draw it like this. A is my lattice parameter for my unit cell. So basically, I want to know, so A is equal to 2RY, right? Which I have, 200 picometers plus 2Rx. And I could solve my A by knowing this distance, because this is 1, 2, 3, 4 RY. Anyone get an answer? Okay, 82.8 picometer. So what if I told you that, so that's the minimum it needs to be. If it were smaller, if X positive had a radius smaller than 82.8, then it could not occupy the rock salt structure. It would have to have a different structure, because the rock salt structure would not be stable if X was smaller. But we run some experiments, look under the electron microscope. We see that X actually has a diameter of 100 picometer. So solve for A. What is the lattice parameter of XY if X has a radius of 100 picometer? Pretty easy, so I can draw it this way. Not to scale. But we see that this is 200. This is 100 plus 100. This is 200. So A is 600 picometer. right? So the unit cell will have a lattice parameter of 600 picometer. In this case, square root of 2a is no longer equal to 4 times r of y. You can't use this middle line, diagonal, to calculate for the size of y anymore because there's some space in between, right? They're not touching anymore. And the reason why they're not touching is because the cations are kind of propping the unit cell open. If you were to remove all of the cations, then yes, they would be next to each other. So I have another question. I told you earlier that this structure is not stable, right? Because the anions are touching each other. If I were to remove all of the cations from this structure, then y would all be touching each other again. How come that is stable, but that's not stable? If we removed all the cations, we would have this structure, right? And this is stable. This is what y would look like. But this is not stable. If you have a cation, that means there's some electron transfer between the cation and the anion. So these are all negative charged, and these are all positive charged, right? If you don't have a compound, if it's just y by itself, there's no charge. It hasn't lost or gained any electrons. So there's no electrical repulsion between the atoms here. So it's fine touching each other, being next to each other, okay? It's only when you have a transfer of electrons, then they become ions, and the ions need to have charge balance. So we know, based on this example here, that the structure of ceramics, right, there's some minimum size that X has to be in order to be in that structure. If it were smaller, it would have to be a different structure. And so there's a table in your book that lists this, but I'll just show you some of it. So if our cation to anion ratio is less than 0.155, so we have a very, very small cation compared to our anion. It would look something like this. You couldn't fit another anion over here, because then the anions will be overlapping, they will repel each other, and will not be stable. So this has a coordination number of 2. So the cation has 2 nearest neighbors, and the anion also has 2 nearest neighbors. And then if you had a slightly bigger cation, it's between, then you have a coordination number of 3. And it'll look something like this. And then between 0.225 to 0.414, you have a coordination number of 4. For our material, what is our coordination number? My Rx. Or what is my ratio? So how many nearest neighbors does my cation have? The edge ones. Okay, let's just take this edge one. You have another unit cell on top, and you have 2 more in front, right? Okay. So with the unit cell within here, you have 1, 2, 3, and 4, this face one. So it's connected to these. And then it's also connected to the face one in here and the face one in front. Okay, so it has a coordination number of 6. So if you look at the table, between 0.732 to 1, the coordination number is 8. And I'll show you some pictures because that'll make a lot more sense than just these numbers. All right, so this first one is what we had talked about before already, what we've been looking at, the magnesium oxide. It also happens to be an NaCl, so salt. Sodium chloride has the rock salt structure. 2 face-centered cubic overlapping. Chlorine here is the bigger atom because it's an anion. Sodium is a smaller atom here because it's a cation. And if you look, this is the stick and ball model. This makes it easier to see the entire unit cell. But if it were in real life, it would look more like this. All the atoms are touching, right? The cation and the anions are touching. And it's a little easier, hopefully, to see that something like this face-centered one has 6 nearest atoms. It has 1, 2, 3, 4, the one in the back and the one in the front. So it has a coordination number of 6. So that's called the rock salt structure. Okay, and then you have a cesium chloride structure, and that looks like this. It's also 2 cubic structures that overlap. Can you tell me which cubic structure this is? What is this structure called? Simple cubic, right. It's not body-centered cubic because the atom in the middle is not the same element as the atoms on the corners, right? So whenever we look at a structure, we only look at the structure for a single element. So this is simple cubic. You only have atoms on the corners. You don't have anything, you don't have that same atom in the center. So this is 2 simple cubic that overlap. What is the overlap? If you were to use the same nomenclature, the same way I described the FCC overlapping by 0, 1/2, 0, how does the cesium chloride simple cubic overlap? Right, so if you look at that back corner, if we assume that this atom would have been in the back corner, it's shifted by 1/2, 1/2, 1/2. And you can see here's one simple cubic. Here's another simple cubic, right? 2 simple cubic structures that overlap, right? And we'll continue about ceramics Friday, tomorrow.